March 1945. A field outside Bielefeld, western Germany. Wreckage of a shot-down Lancaster bomber scattered across frozen mud. German Luftwaffe engineer Walter crouches beside a twisted engine mount. The data plate reads Rolls-Royce Merlin, the same engine he saw on down Spitfire fighters over the channel. Pulls out his field notebook. Lancaster empty weight 30,000 pounds, full combat load 68,000 pounds, Spitfire weight 6,000. 100 pounds, 10 times lighter, both aircraft using identical Rolls-Royce Merlin engines. He checks the serial numbers twice, not a different variant. The exact same that pushes a 3-ton fighter to 600 kilometers per hour is somehow lifting a 30-ton bomber carrying 10 tons of bombs. His report to the German Air Ministry includes one line: data appears incorrect, physically impossible for single engine type to power both aircraft categories, but the numbers are real. The British have been flying Lancaster missions over Germany every night for 3 years. The solution began 4 years earlier, when engineer Roy had faced a desperate problem. The Manchester bomber was killing its own crews with engine failures. Had 3 months to fix it, or the program would be cancelled. His answer seemed insane. Throw out the powerful engines and install 4 weak ones instead. 4 Merlins, fighter engines on a heavy bomber. The Manchester was supposed to be Britain's answer to Germany's bombing campaign. Aircraft designed it in 1939 around 2 Rolls-Royce Vulture engines. Each Vulture produced 1,760 horsepower, powerful on paper. Catastrophic in reality. The Vulture was essentially 2 Rolls-Royce Peregrine engines joined at the crankcase, complex, prone to connecting rod failures, oil leaks, overheating. On November 25, 1940, Manchester serial number L7320 lifted off from RAF for a night training flight. 3 minutes after takeoff, the port Vulture caught fire. The aircraft crashed into a field. All 7 crew members died. It was the 9th Manchester lost to engine failure that year, not to enemy action, to its own. By spring 1941, the Royal Air Force was losing Manchester bombers faster than factories could build them. 79 aircraft lost to accidents and mechanical failure out of 200 produced. Pilots called it a death trap. The Air Ministry issued an ultimatum to Chief Designer Roy: fix the Manchester or the entire program gets cancelled. 3 months, no extensions. Solution violated every principle of bomber design. Instead of fixing the Vulture or finding a more powerful engine, he proposed removing both Vultures entirely and installing 4 Rolls-Royce Merlins, fighter engines. The Merlin produced 1,280 horsepower, 24% less power than a Vulture. Chief Engineer Stuart Davies laid out the math during an April meeting at its facility. 2 Vultures, 3,520 total horsepower. 4 Merlins, 5,120 total horsepower. But Davies pointed out the problem. 4 engines meant 4 times the weight of engine mounts, 4 cooling systems, 4 sets of controls, 4 propellers. The additional drag and weight would offset any power advantage. And Merlins were designed for high-altitude sprint performance in fighters like the Spitfire, not sustained cruise power hauling bomb loads. Knew the numbers looked wrong, but he also understood something about engine distribution that the calculations missed. Weight matters less than where you place it. The Manchester's 2 Vultures sat close to the fuselage. When one failed, the asymmetric thrust made the aircraft nearly uncontrollable. 4 Merlins spread across a wider wingspan would balance thrust even if 1 or 2 engines quit. And Merlins had one advantage Vultures never achieved: reliability. Spitfire squadrons were flying Merlins through sustained combat operations. The engine worked. The precedent existed. Boeing's B-17 Flying Fortress had been operational since 1938 with 4 Wright Cyclone engines. But those were Wright Cyclones, specifically designed for bombers. Large radial engines built for endurance. Nobody had ever put a liquid-cooled fighter engine on a heavy bomber. The thermal management alone seemed impossible. Merlins ran hot, pushing Spitfires through high-speed climbs. A bomber required sustained cruise power at lower altitudes with heavier loads. The cooling system would need complete redesign. Proposed synchronization as the answer. 4 engines working independently created vibration that would tear the airframe apart. 4 engines synchronized to within 50 revolutions per minute became a single system. The propellers would turn in precise coordination. The power pulses would align. The airframe would experience smooth, distributed thrust instead of 4 competing forces. He'd already calculated the wing modifications needed to handle the additional engine weight and span. The Manchester's wing measured 90 feet 1 inch. The new design would extend to 102 feet. More surface area to generate lift, better weight distribution for the outboard engines. The additional wingspan would reduce wing loading, the amount of weight each square foot of wing had to support. Davies remained skeptical. If this solution was so obvious, why hadn't anyone else tried it? Response was direct, because everyone else was trying to build more powerful engines. He was building a more intelligent system. The Air Ministry approved the prototype in May 1941, had 8 months to prove 4 weak engines could outperform 2 strong ones. The first test flight was scheduled for January 9, 1942. If the aircraft failed, Britain would enter 1942 without a heavy bomber capable of reaching Berlin. January 9, 1942. Aerodrome, Cheshire. The Lancaster prototype BT-308 sat on the tarmac under grey winter sky. 4 Rolls-Royce Merlin 20 engines mounted on wings that looked disproportionately long for the fuselage. Chief Test Pilot Sam Brown completed his pre-flight walk-around. He'd flown the Manchester. He knew what happened when engines failed on takeoff. This aircraft had 4 of them, 4 points of potential failure. But also 4 sources of thrust if the synchronization worked. Brown advanced the throttles. All 4 Merlins spooled up together. The propellers bit into cold air. BT-308 accelerated down the runway. Rotation speed, 105 miles per hour. The aircraft lifted smoothly. No vibration, no asymmetric pull. Brown climbed to 8,000 feet and began testing engine-out procedures. He throttled back the number 2 engine. The aircraft remained stable. He throttled back number 3, still controllable. With 2 engines on one side producing 0 thrust, the Lancaster held altitude and responded to control inputs. The Manchester would have been in a death spiral. The key was the wing. Hadn't just added 2 more engines. He'd redesigned the entire lifting surface. The Manchester's wing measured 90 feet across with a chord of 17 feet. The Lancaster's wing stretched to 102 feet with the same chord depth. That additional 11 feet of span changed everything about how the aircraft distributed weight and generated lift. Wing loading is the amount of weight each square foot of wing must support. The Manchester with full bomb load carried 63 pounds per square foot. The Boeing B-17, considered one of the best designed heavy bombers, carried 38 pounds per square foot. The Lancaster carried 67 pounds per square foot. Higher than the Manchester despite the larger wing because had increased maximum takeoff weight to 72,000 pounds. Higher wing loading should have made the Lancaster a dangerous aircraft to fly. Heavy wing loading means higher stall speeds, less margin for error on landing, but compensated with wing shape. The airfoil profile generated maximum lift at the specific speeds and angles a loaded bomber operated. The Manchester's wing was designed for 2 powerful engines providing brute force. The Lancaster's wing was designed for 4 synchronized engines providing distributed thrust. The difference wasn't just mathematical. It was aerodynamic philosophy. The cooling system solved the thermal problem everyone said was impossible. Fighter pilots pushed Merlins to maximum power for minutes at a time. Bomber operations required cruise power for hours. Different thermal loads, different cooling requirements. The Lancaster mounted radiators in housings under each wing between the fuselage and inner engines. Air flowing under the wing at cruise speed provided continuous cooling. The system included intercoolers to reduce intake air temperature and oil coolers separate from the main radiators. Each engine ran independently but within tolerances that kept all 4 at matching temperatures. If one engine started running hot, the pilot could adjust its mixture and throttle, while the other 3 maintained cruise power. Synchronization was mechanical. Each engine drove a propeller through a reduction gearbox. The propeller governors maintained constant speed regardless of throttle changes. Brown could set all 4 engines to 2,400 revolutions per minute, and the governors would hold that speed within 50 RPM. 50 RPM difference was the threshold. Beyond that, the propellers created standing waves in the airframe. Vibration built up, metal fatigued, but within 50 RPM, the 4 engines became one system. The power pulses from each cylinder firing aligned closely enough that the airframe experienced smooth thrust, instead of oscillating forces. Brown landed BT-308 after 2 hours and 17 minutes. His report contained 2 words that changed Britain's bombing campaign: no vices. The aircraft had no handling quirks, no dangerous tendencies, no surprises. It flew like a stable, predictable heavy bomber despite using fighter engines. The Air Ministry placed an order for 3,000 Lancaster bombers in February 1942. By March, the first production aircraft rolled out of its factory. By April, No. 44 Squadron received the first operational Lancasters. By May, they were bombing Germany. And German intelligence officers started finding Rolls-Royce Merlin data plates in the wreckage of bombers that shouldn't have been able to fly. By 1944, Barnes had a problem that required physics most engineers considered impossible. Was the designer behind the dam buster bouncing bomb that breached the and dams in May 1943. Now he wanted to create something that didn't bounce, something that penetrated. An earthquake bomb, 22,000 pounds of high explosive in a single streamlined casing. The weight alone exceeded anything the Royal Air Force had ever dropped. The largest operational bomb in 1944 was the 12,000-pound Tallboy. Wanted to nearly double that. The problem wasn't building the bomb. It was finding an aircraft capable of carrying it. The Lancaster's maximum bomb load was 14,000 pounds. Grand Slam weighed 22,000. Even if you could physically fit it in the bomb bay, the aircraft's structural limits couldn't handle the weight. The wings would fail. The landing gear would collapse. Needed the Lancaster, but the Lancaster couldn't do what he needed. Engineers modified 23 Lancaster B Mark I airframes into special variants. They removed the nose turret, removed the mid-upper turret, stripped out armor plating, cut open the bomb bay doors and reinforced the surrounding structure. The modifications reduced empty weight by several thousand pounds and created clearance for the 22,000-pound bomb. Even with the weight savings, a Lancaster special carrying Grand Slam operated at 72,000 pounds gross weight, 8,000 pounds over the original design limit. March 14, 1945. Squadron leader Charles lifted off from RAF Spa in Lancaster PD-119. Grand Slam hung in the modified bomb bay. Target, Bielefeld Railway Viaduct in Germany. The viaduct carried the main rail line supplying German forces in the Ruhr. Previous raids with conventional bombs had damaged but not destroyed it. Climbed to 18,000 feet. The 4 Merlin engines pulled the overloaded Lancaster higher than most bombers operated. At 14:30 hours, the bomb aimer released Grand Slam. 22,000 pounds fell for 41 seconds before impact. The viaduct collapsed. Over 100 yards of structure dropped into the valley below. When returned to Spa, ground crew inspected PD-119. The wing main spars showed visible deformation from the extreme weight. Metal stressed beyond normal operating limits. The aircraft had flown at the absolute edge of structural failure, but 4 Rolls-Royce Merlins had lifted it. The same engines that powered Spitfires to intercept German fighters at 25,000 feet had just hauled a 30-ton bomber with a 10-ton bomb to target and back. German intelligence analysts received reports of the new super bomb. They recalculated the numbers. The math still showed it was impossible. German aviation doctrine operated on specialization. Fighter engines for fighters. Bomber engines for bombers. Transport engines for transports, each designed for a specific mission profile. The Junkers 211 powered medium bombers like the 111 and Junkers 88. The BMW 801 went into the 190 fighter. BMW radials powered the 200 Condor maritime patrol aircraft. No crossover. No adaptation. The idea of putting a fighter engine on a heavy bomber violated the fundamental logic of German engineering. The 177 demonstrated what happened when Germany tried to break that rule. The Air Ministry wanted a heavy bomber with range to reach Britain and speed to evade fighters. Solution: 2 engines, but each engine was actually two 605 inverted V12 engines coupled together. The DB606 produced 2,700 horsepower, powerful enough for a heavy bomber. The coupled design saved weight and reduced drag compared to 4 separate engines. On paper, it solved everything. In operation, the DB606 caught fire. Constantly, the coupled crankshafts created harmonic vibrations that cracked engine blocks. Cooling systems failed. By 1944, the He-177 program was effectively cancelled after losing dozens of aircraft to engine fires. Britain took the opposite approach. The Merlin wasn't designed for one mission. It was designed to be adaptable. Rolls-Royce produced Merlins for Spitfires, Hurricanes, Mosquitoes, Lancasters, and even the American P-51 Mustang. The same basic engine architecture scaled across every role. Different supercharger configurations for different altitudes. Different reduction gearing for different propeller speeds. But the core design remained constant. Reliable. Proven. When needed 4 engines for the Lancaster, he didn't need to wait for a specialized bomber engine to be developed. He used what already worked. By May 1945, Lancaster bombers had flown 156,000 sorties, dropped 608,000 tons of bombs, 7,377 aircraft built. The same Rolls-Royce Merlin that pushed 3-ton Spitfires to 600 kilometers per hour had lifted 30-ton Lancasters with 10-ton Grand Slam bombs across Germany every night for 3 years. German engineers called it physically impossible because they calculated the power of 1 engine. They missed the system of 4. Sometimes impossible is just something you didn't think through completely, and your enemy did. The history of World War II aviation is filled with moments where conventional thinking lost to unconventional engineering. If this story changed how you see the impossible, leave a comment about which wartime technology you want explored next. And if you haven't subscribed yet, hit that button. There are more stories like this one waiting.